Okay, so good morning, ladies and gentlemen. Welcome back to today's morning session of the school come workshop on data analysis in cosmology and astroparticle physics. Today, Professor Suman Majumder will continue his discussions on 21 cm cosmology, and he'll be giving two lectures, both in the morning session and in the afternoon session. Okay, over to you, Suman.
Thank you, Supradigda, for the introduction. So today I have decided that we will briefly discuss something initially, and then we will get into the hands-on, because I think I'm lagging behind in terms of the hands-on part of these workshop. So there are quite a lot of things that I want to cover in the hands-on session. So first I will just cover a little bit of science to start with, and because that will be useful for the hands-on session, and then I will switch to the hands-on. So let's say it will be 20 minutes of discussion initially, then an hour of hands-on in the morning. In the afternoon, again, I think I will do the same. I will do a 20 minutes kind of discussion that will lead to the hands-on session that hopefully will be an hour or more, as long as you need, means depending on your proficiencies. And I will be using the Psi server, and I looked at the discussion in Slack channel. There were some issues with the Psi server, but I actually have tested it quite a few times, so I am hoping that things will go smoothly. You have to initially follow my instructions religiously, means without any question, and then once those steps are done in your own individual accounts, then I think things will work out. So and I will explain why I did, or why I am asking you to blindly follow first few steps in the Psi server. Okay, I will explain that later. But if things do not run, then it's very frustrating for all of us, and it's kind of becomes an hindrance in understanding certain things. Okay, so without any further delay, let us start the discussion. I will share my screen. Yeah. Yes. So I hope you can see the same old slide that with which I kind of started yesterday. So today I will focus our discussion mostly in the epoch of reionization. So yesterday we discussed, when we ended the discussion, we were discussing mostly about 21 cm signal that is coming from the epoch of reionization, right? 21 cm signal from neutral hydrogen. How this can be detected, how one can basically understand the sky average 21 cm signal as a function of observed frequency or cosmological redshift that many global signal experiments are trying to detect, or they are also popularly known as monopole experiments, because they probe the monopole of the signal, that is the mean value of the signal. They do not care about the spatial fluctuation at a given redshift. Then there are these radio interferometers, which are targeting to probe not only the time evolution, that is the redshift evolution of the signal, which the monopole experiments do. On top of that, they also want to probe the spatial fluctuation at a given redshift. Sorry. So that now, if I just look at this same figure once more, and try to understand from where this 21 cm signal is coming. So the 21 cm signal is coming from these so-called YOLO parts in this artist's impression of what has happened during the epoch of reionization. So the YOLO part is essentially the space between the galaxies. So because the ionizing radiation that was being emitted by these galaxies, they will mostly ionize the the hydrogen, neutral hydrogen, that is in the close proximity of the galaxy. So it is only the space between the galaxies where neutral hydrogen will remain at a substantial, let's say, time scale during the reionization. And eventually they will also ionize, obviously. By that time we reach these parts where the space between the galaxy is also fully ionized. And then we said that the hydrogen will only remain within those neutral collapsed, sorry, the damped Lyman alpha systems, or those highly dense neutral hydrogen clouds which can self-shield themselves from the background of ionizing radiation or background of ultraviolet radiation. However, as you can see, there is a fallacy in this whole business, because though we are claiming that one would be able to probe the properties of galaxies, what kind of spectrum they had, what type of what type of, let's say, what type of photons they have emitted more, whether they were X-ray photons or ionizing, so UV photons, etc. Um, we are we essentially claimed that all of that can be done using just this, just by probing this hydrogen distribution in between the galaxies. But I am nowhere we are actually planning to, in this particular business, we are not planning to probe the galaxies themselves. Because if I manage to see the galaxies themselves, then I will be able to say something about these properties that we are trying to indirectly infer from the intergalactic medium, or the gas in the intergalactic medium, right? So the other approach, or a complementary approach of observing this epoch of reionization, could be to seeing the galaxies themselves, observing the galaxies themselves. Now, there is another problem. Why people haven't tried that extensively? Actually, people have tried it extensively with the existing, let's say, telescopes. So you will hear the highest redshift galaxy that has been, I'm sorry for the noise because of the rain here. Let me just close everything. Just a second. Sorry. So I hope now the background noise is slightly less. So what people have tried so far is to detect these very high redshift galaxies using various kinds of line emission that are coming out of them. So just like the 21 centimeter line, because it's a line emission, it will have a specific line profile. It's not a continuum emission. So it's not the spectrum of a line will look like a, let's say, it will have a line profile, and you can follow it over the redshift. So it will get redshifted to another wavelength, and using the line profile, you can effectively detect it. Now, there can be several such lines that are coming from these galaxies. And one such line actually we discussed yesterday while discussing the optical depth. So many galaxies actually emit huge amount of Lyman alpha photons. But the problem with Lyman alpha photon, we discussed yesterday as well, that it has a very, very high optical depth. So the moment it is emitted, so let's say from this particular galaxy, or let's say this particular galaxy, if some amount of Lyman alpha photon is being emitted, it will readily, or the blue portion of its spectrum will get readily absorbed. There won't be any part of the spectrum visible by the time the radiation passes through this hydrogen, this particular part of the intergalactic medium, because you just need 10 to the power minus 4 neutral fraction to absorb all of the Lyman alpha. So they are, so it will be difficult for you to tell about the state of the intergalactic medium just by looking at the spectrum. And as a significant part of the spectrum will be wiped out, will turn into basically a black patch, it will be difficult for you to say anything about the galaxy's property itself, right? So there have been several efforts where people using, let's say, Earth-based telescopes, as well as followed it up using Hubble ultra-deep field observations. People have tried to basically see very distant galaxies, and that's how very high redshift galaxies were detected spectroscopically. Initially, they are detected through photometry, and then they are kind of, their redshift were confirmed mostly by spectroscopy. So I think the highest redshift galaxy that we know so far is somewhere around redshift 10. If I am not completely wrong, so one has to check that. So, and the highest redshift quasar is somewhere around, because quasars are brighter than galaxies, so the probability of seeing them becomes higher. Okay, one more point of, or one more problem in probing high redshift objects is that the farther away it is from you, the older it is, right? That is what is happening. The distance essentially turns out to be the finite light travel time that the photons take to reach from its source to you. By that time, universe ages, right? So when those photons were emitted, universe was younger compared to when you observe them. So the farther away you go, or the farther away the source is, the, let's say, the earlier stage of the universe you are looking at. So the farther away the source is, one more thing happens to the intensity that you receive from the source. It becomes dimmer and dimmer. So it becomes difficult with your existing experiment, with the existing sensitivity of your telescopes, to probe those objects. So that's another problem that comes into play. One is that most of the spectrum gets wiped out, and the second is the objects get fainter and fainter the further away they are. So there are many line emissions which are basically associated with the particular, let's say, nature or characteristics of these galaxies that we would like to probe. So what we would like to probe, let's say I want to know what was the role of these galaxies in reionization. Let us imagine that is my science goal. So if that is my science goal, I need to know how much ultraviolet photon a particular type of galaxy had produced, right? So how would I know that particular type of galaxy have produced? What is the main mechanism of production of this ultraviolet photon? Star formation. The more star formation that happens within a galaxy, the more ultraviolet photon it produces. Now, how do I know that a galaxy is having lots of star formation? So then there are some sort of associated line emission from the galaxies that I can target. One such line emission is this singly ionized carbon line. And people have seen that in the local universe, that is, universe around, in the galaxies around us at the present day, actually, people have seen that the active star formation in a galaxy has a proportional kind of relationship with the luminosity of the galaxy in C2 line, or C2 luminosity of the galaxy. C2 is singly ionized carbon. That's spectroscopic notation of that particular line. So people have conjectured that I can use this particular line as a proxy for star forming activity, or the luminosity of this particular line or strength of this particular line as a proxy of star forming activity within the galaxy, right? But again, this particular framework is based on several assumptions. First of all, we have seen it only in our local universe, right? And we do, obviously, when people have correlated the luminosity of C2 with the star formation, specific star formation rate of a galaxy, they had assumed some sort of physical model between these two quantities, or related these two quantities via certain physical model. Now, no one knows whether that physical model, first of all, is valid in the early universe when we look at very early type of galaxies or quite primordial galaxies, whether that holds true or not. Second, because early type of galaxy might be might have different kind of environment altogether. So that environment, or let's say the level of metal that is there in a present day galaxy, might not be there in the early type of galaxy. So now how much we can extrapolate this particular model of star formation rate, relationship between star formation rate and the C2 luminosity, that can be basically debated, and that can be questioned all the time, because we do not have enough data at high redshift. Because, as I explained earlier, it is very difficult to observe these galaxies at high redshift. So you need to have two independent observation, one which will probe your star formation rate, and the other one which will basically probe the luminosity of the C2 galaxies. Sorry, C2 line. So it's quite difficult to achieve that. So most of the present studies are actually, that's why, based on these sort of empirical relationship that people have built by observing the present day galaxies. Now, based on certain, let's say, physical models, people have tried to simulate these early, very early type of galaxies, which might be more responsible for ionization of hydrogen in the early universe. And while doing so, they essentially reduced the metal content of these galaxies compared to the present day galaxies, etc., and so on and so forth. And they allowed the physical processes to take their own course and evolved them with time, and had looked at how these C2 luminosity varies with the specific star formation rate with cosmological redshift in these kind of galaxies, or how these galaxies, what is the lifetime of these galaxies, these early type of galaxies, and how they die and new kind of galaxies are formed in the same, in a modified environment, etc., etc. However, those simulations also have certain kind of limitation, simply because of the fact you are trying to, in principle, you would like to basically build a simulation which starts from the very basic principle. There you essentially produce a photon and follow the journey of the photon until it's completely consumed by within the galaxy's environment or within the intergalactic medium's environment. But that is not necessarily very easy to do, simply because of the fact, I think Tirthoda has explained it in detail, that we are basically dealing with a problem which has a very high dynamic range. Because if you are trying to simulate the galaxies, you need to resolve the galaxies, which is of the order of kiloparsec. And you want to see their effect on volumes which are as large as a gigaparsec cube. Sorry. So starting from, sorry, yeah, somebody have a question, I guess, and there was a feedback from my end, I think. So starting from kiloparsec scale, length scale, going to gigaparsec, or if you look at it from the mass scale of the problem, starting from the mass of a galaxy, going to a cosmological volume where you essentially are holding billions and billions of galaxies, it becomes very difficult even for these kind of simulations, and become computationally intensive and time consuming. So at the end of the day, people take up these empirical relationships that we observe in our local universe, and based on some physical assumptions, they try to extrapolate it to the high redshift. And that's how you can model what kind of radiation you should expect from these early galaxies. Now, when it comes to practice, that when you want to actually make an observation using this C2 line of an early galaxy, then it becomes again difficult, simply because of the fact that I had already mentioned, that these early or high redshift galaxies are very faint. So it's very, very difficult using the present day or even upcoming telescopes, which will operate in far infrared, to detect these lines in very early galaxies. So people came up with an alternative approach. And this alternative approach is similar to what we do with the hydrogen gas in intergalactic medium while observing it using 21 centimeter line. So we are not interested in very small parcels of gas. We are actually interested in observing the intensity that is coming from, let's say, a 1 megaparsec cube or 2 megaparsec cube volume of parcel of gas. So I don't need to resolve my images less than 2 to 3 megaparsec, let's say, in terms of, let's say, 2 cube megaparsec resolution. Because if I do that, then the intensity of each pixel, intensity of 21 centimeter line in each pixel will be very low and I won't be able to detect it. I will need very long observation time to have a significant amount of statistically significant amount of signal in 1 pixel of my image, if I think about it in terms of image. But remember, we are not observing 21 centimeter line in image plane, we are observing them in Fourier plane, and we are recording something called visibility, which is the brightness temperature of Fourier transform of the brightness temperature of that particular line. So a similar approach can be taken while observing the C2 line emitted by these early galaxies. So I may say that, okay, I don't care about resolving each individual galaxy and look at their spectrum. All I care is, let us say there is in my sky, there is a 2 cross 2 megaparsec square pixel at a specific redshift. And all I care is that how much C2 intensity is coming out of that particular pixel. Now, that particular pixel may have 2 galaxies or 200 galaxies or 2000 galaxies. I don't care. I don't need to resolve them. All I want is the integrated intensity of C2 line that is coming from that particular pixel at the redshifted frequency of that specific line. So this can be done not only for the C2 line, it can be done for various other lines which are thought to be associated or thought to have some sort of correlation with the star formation rate within that galaxy. Because I am interested in the star formation rate. I am interested in knowing the star formation rate simply because of the fact if there is star formation activity, it will produce lots of ultraviolet photons, and those ultraviolet photons will take part in reionization. So I want to know which type of sources were dominant in producing the photons or ultraviolet photons necessary to complete the reionization by a certain redshift that our 21 centimeter observations will tell us, right? Or other observations will tell us. But I want to know directly the properties of the sources by looking at the sources directly. And here the approach is, we don't have to resolve the individual sources, but all we care about within a certain resolution element on my sky, if I can detect the integrated brightness of this particular line. Okay, so that will give me a coarse gridded map or coarse gridded distribution of these galaxies on my sky at a specific redshift, given that I tune my observing frequency accordingly. Okay, so that particular idea that I don't need to resolve individual galaxies, but all I care is the integrated intensity or brightness of C2 line that is coming within a pixel, within a coarse gridded pixel in the sky, is called line intensity mapping. Okay. So, yeah. So you may have several.
I have a question.
Yeah, please go ahead.
Sir, here early galaxies means that the galaxy contain population 3-star or late galaxies?
Okay, so that I have kept ambiguous because of the fact that, let's say, if I am looking at the galaxies or if I have tuned my observing frequency in such a manner that I am looking at the edge of the reionization, so where reionization is almost at the very late stage and maybe within a redshift interval of 0.5 or 1, it is going to end. So those galaxies might have, means though for cosmologists, they may look like, let's say, redshift 7 or redshift 6. For a cosmologist who is probing reionization, that might be a low redshift, but for those who are actually observing galaxies, they consider those galaxies at very early galaxies. Okay. And I am not necessarily saying that you will be able to probe these population 3 stars or the very first sources of light by this particular technique. In principle, you can, if those galaxies or those stars also produce C2 line. In principle, you can, but they may not, because they may not have the metals, they may not have produced the metals yet. So the population 3 stars will not be producing C2 lines. But the assumption or most of the models for reionization more or less assumes that they die out after a very short span. And then second generation of population 3 stars are produced, which use a different kind of cooling mechanism. And then population 2 stars are produced, so on and so forth. So with this technique, probably we will be able to probe the galaxies in the range of, in the redshift range, let's say the redshift 10, 12 to redshift 6 or 5, something like that. Okay, so they are already little bit evolved galaxies which are already using metals to cool for the cooling mechanism essentially. Okay, so how does this particular line, so how does this particular line originates? So it is via the transition from 2p 3 by 2 to 2p half, these two states, and the rest frame frequency for C2 line is 158 micrometer, or 1900 in frequency it will be 1900 gigahertz. So it's very high frequency observation compared to, let's say, the 21 centimeter observations. And this is one of the brightest line in star forming galaxies. So one assumes that it has some sort of correlations, and people have built up physical models where you will find that there is a strong correlation between the star formation rate or specific star formation rate in a galaxy and the luminosity of the, or brightness of the C2 line. And there are already some surveys where individual galaxies, these are not line intensity mapping surveys, these are done using a telescope in Atacama Desert, where people have targeted, done targeted observation of very bright the galaxies in the redshift range 4 to 6, though they are not very many, but I think more than few hundred has been detected already using their C2 lines. So it is kind of a proven technique in a universe where reionization has finished or almost at the late stage. Okay, and right now, actually, several new experiments are coming up where which will actually employ this particular line intensity mapping technique to do or map out the sources of reionization or sources of ionizing photons, so as to say, at high redshift. So again, the target redshifts, for example, this particular experiment called Concerto, which will be installed in the Apex telescope in Atacama. The target redshift range is 5.1 to 8.5, something like that. And then there are other telescopes, for example, CCAT Prime, Time Pilot, etc., which will also target a similar kind of redshift range, 5 to 9, to observe the early galaxies using line intensity mapping with C2 line. So now the question is, let us say you have observations of these early galaxies through line intensity mapping, and you have observations of the hydrogen that is distributed in between them through 21 centimeter maps in some way. So now what kind of extra information that you can get from these two independent experiments, observations, surveys, whatever you may call them? So one way of basically looking at them or combining them or extracting more information out of them is to do cross correlation between them. So what does the cross correlation will tell us? So what do you expect? Let us go back to that image once more. So see, the C2 line will come from these galaxies, right, which are sitting at some sort of ionized region. And the 21 centimeter line will come from this intergalactic medium, which is in between the galaxies. It will not come from the, let's say, the holes where galaxies are sitting, the ionized holes or ionized space from where galaxies are sitting right now. So apparently, if you just use your common sense, and if you think of any kind of cross correlation, you would imagine that these two signals will be anti-correlated. The location from where I am expecting my C2 line, I would not expect 21 centimeter line to come from, or 21 centimeter signal to come from the same location. Now, the degree of this anti-correlation can tell you something more. And how this anti-correlation evolves with redshift, that may also tell you something very interesting. So let's say if I am able to see the universe using C2 intensity mapping by up to this line, let us draw it here, let's say up to this line, and my basically C2 survey kind of lasts in this range. So I can basically map out the universe using C2 line in this kind of redshift range. And in the similar redshift range, I also have 21 centimeter observation. So when I will start, let's say if I take this amount of chunk of my data, I divide my data into several chunks of redshifts, right? I can do that always. So if I do that, then something interesting will come up. And I basically decide these chunks or width of these chunks along the redshift axis or the line of sight axis, taking into the fact that the signal to noise ratio for this C2 intensity mapping is high enough that they are still detectable, etc. And I cross-correlate the C2 map with the 21 centimeter map within this chunk, and so on and so forth. So what would be the degree of anti-correlation when we start here? The degree of anti-correlation might be very low at this stage, because see, the H1 or 21 centimeter signal will come from almost everywhere, just except few points where the C2 line is there. But if I compare it with the last kind of chunk, there the degree of anti-correlation, or actually it might be very high here, and at the late stage the degree of anti-correlation might be very low. So by looking at the degree of this correlation, cross correlation, whether it is positively correlated or negatively correlated, and to what degree they are correlated, I can actually tell something about the state of hydrogen as a function of redshift, the global state of hydrogen as a function of redshift from these cross correlation done in this kind of small redshift intervals. So in other words, I can say something about the history of reionization from these kind of cross correlation studies. So that is something unique that I can say by combining these two information. I can probably infer something about the history of reionization from each of these observations independently, most likely from the 21 centimeter signal observation independently, but that will have much higher uncertainty compared to the cross correlation studies that I will do. Okay, so that is the main motivation of doing these intensity mapping observations of the early universe, to do cross correlation and the level of cross correlation will also vary depending on the length scale at which we are looking at. So at sufficiently large length scale, probably things will be anti-correlated, maximally anti-correlated, but at small length scales, they might not be that anti-correlated, and we will see how these things pan out eventually. So now to interpret one such, let's say, cross-correlation observation or autocorrelation observation, again, you will need some sort of model for your C2 intensity mapping signal, how this signal evolves with time, right? And one, I think I have given some hint that I can take the empirical relationship that I have with some sort of modification for C2 luminosity with let's say star forming efficiency in a galaxy, and relate that to the mass of the halo that is hosting that particular galaxy. So now I will have a relationship between the C2 luminosity and the mass of the halo. okay, which is hosting the galaxy. Now, using this relationship, I can build up or simulate the expected C2 intensity map from a certain redshift for a set of model parameters that I have used to model the C2 luminosity in the first place. And that is precisely what people do actually. So what people do essentially, because these galaxies are located in biased location in my dark matter distribution. So people would first like to simulate the dark matter distribution. And I think Tirtha has already told you that you can do that by various ways. There are these quicker methods. For example, you can do quicker but approximate methods. For example, you can do a Zeldovich approximation and extrapolate at very high redshift and then extrapolate it to a lower redshift, and you get your distribution of matter, and then you identify the collapsed objects in the distribution of your dark matter. And those collapsed objects you identify as the halos, dark matter halos, which will host the galaxies, which will produce ionizing photons. So you can have a halo mass function where essentially the number densities of halos will be plotted on the y-axis as a function of the mass of the halo in the x-axis. This is something I think Tirtha has taught you in the first large-scale structure lecture, most likely. So you can simulate that as well. So on top of that Zeldovich approximation, if you want to do it more accurately, if you want to generate the dark matter distribution more accurately, what you can do is you do the Zeldovich approximation and you basically you produce the initial density fluctuation at very high redshift, and then you allow the dark matter particles to evolve with time or move around with time under gravity, and finally at lower redshift you find your distribution of matter. So that is done using these n-body simulations. So n represents a large number of particles, that's why they are called n-body simulations, where you essentially calculate the force between each individual dark matter particle at small time steps. And once you get your final dark matter distribution, you can identify which are the clusters of dark matter particle that can be marked as collapsed objects, and you identify them as dark matter halos. You can use various kinds of algorithms, for example, spherical averaging technique, friends of friends algorithm, etc. So here I have given an example of a n-body simulation and a FOF halo identification technique, which we will discuss in the hands-on session as well, to identify these halos. Now, what you can do, you can, as I was saying, that C2 luminosity is associated with the star formation activity within each individual galaxies. Now you can assume that a particular dark matter halo may host, depending on its mass, a large number of galaxies or a certain number of galaxies. You can basically come up with some sort of model, and then you associate the necessary C2 luminosity that is predicted by your analytical model or your empirical model that you have built up so far to that particular halo. So depending on the halo mass, you are associating a C2 luminosity to the halos. So this is done, we do it, particularly in my case, we do it using the models prescribed by Silva et al. In one, basically, the star formation rate is associated with the mass of the halo, or basically the number of galaxies or total mass in the star, in the star in a galaxy, are associated with the halo mass, which is hosting the galaxy. And from that star formation rate, and there is a relationship that one assumes from the empirical relationship that one find from the local universe, that star formation rate is associated with the C2 luminosity. So everything here is represented in terms of solar quantities. For example, here the star formation rate is defined in units of solar mass per year. And the luminosity, C2 luminosity, is also in the units of solar luminosity, etc. So we use these models to assign or paint each individual halo with their corresponding C2 luminosity. Once that is done, then I can do what I can do. I can basically, because each individual halo I will not be able to distinguish, so I do a coarse gridded mapping of those halos, and it turns out to something like this. So at redshift C2, sorry, at redshift 7.2, using these prescription on some halos that we have identified from our in-body dark matter only simulations, the C2 intensity map or C2 line intensity map will look something like this. The units here are Jansky per steradian, and CMPC means co-moving megaparsec. So the X and Y axis are something like 215 megaparsec, co-moving megaparsec on both sides. So it's a simulation cube that you will get. And the darker the point is, the higher the C2 intensity is there. However, this hides, this kind of empirical, simpler relationship hides one important fact. Not all halos, even if they have the same mass, first of all, will have same number of galaxies. And even if they have same number of galaxies, the environment of those galaxies will be different from halo to halo. So if I choose two halos which have identical mass, which have identical number of galaxies, still the line emit or the luminosity of C2 that will come from these two halos should differ in principle, simply because the galaxies might be in different kind of environment, right? And that will influence the total emissivity of C2 line from these galaxies. So there should be, in principle, a fluctuation in this LC to halo mass relationship. And people have tried to simulate this, though, as I was saying in the beginning, that these simulations are very, very time consuming and also computationally intensive. You need huge amount of computational resources, and still they will not be able to cover the entire halo mass range that you wish to cover, or that is let's say practical to cover. They will be able to cover a small halo mass range. So some people came up with these simulations, which they managed to run only for a single redshift, and they figured out the scatter in this C2 luminosity and halo mass from their simulations. And actually these simulations were done in a kind of staggered manner. So there are 3 different volumes, and each volume loses out in terms of let's say mass resolution. So for example, you can see there are 3 clusters of points. One is here, one is here, and one is here. So they represent 3 different simulation volumes. And each of these simulation volumes, actually the smallest one, and this represents the smallest simulation volume, where actually they can probe to the smallest halo mass that is possible to detect. So they go up to almost 10 to the power 9 M-sun halo mass. But they lose out on halo masses greater than 10 to the power 10 M-sun, because they cannot simulate those halos, because they are too, you need larger volume to simulate them, and they basically run out in terms of their computational resources. So what they do, they then simulate a larger volume, but in this larger volume, they do not want to resolve the 10 to the power 9 M-sun halo mass. They restrict themselves only up to 10 to the power 10 M-sun halo mass, and simulate up to 10 to the power 11 M-sun halo mass. So within this halo mass range, they can mimic the physics properly, and they get this kind of scatter. So, and they do the same for the even larger simulation volume, where they restrict their halo mass resolution, halo mass limit from 10 to the power 11 to 10 to the power 12 or 13 or so forth. So in this manner, they have found out this kind of a scatter in the relationship. And in principle, one should include this fluctuation or uncertainty in the C2 luminosity from halo to halo. Even though if those halos have same mass, there should be a significant scatter, which has not been taken into account in this simulation, this particular map that I am showing you here. Okay, so now what our plan is, if I do not have that kind of resources, I have to live with what I have. So I have to find out a science problem that I can solve with this limited resources that I have, right? So the science problem that has motivated us to start with was to understand the level of correlation that is there between C2 and 21 centimeter signal that are coming from the epoch of reionization, right? So Tirthoda has already discussed with you one 21 centimeter or one reionization simulation where you essentially identify collapsed objects from a dark matter distribution, which may have come from either a Zeldovich approximation or Zeldovich plus n-body kind of approach or LPT. There are various other approximate methods to generate a dark matter field actually. And you have identified collapsed objects on it, and then you have populated those collapsed objects with some number of photons which are proportional to their halo mass, right? And these photons are ionizing photons, so ultraviolet photons. And these ultraviolet photons will now go out and using a semi-numerical technique, you will identify the ionized regions, and eventually you will get a ionization fraction map out of your simulation volume, and you will multiply it with the matter density distribution and find out what would be the neutral hydrogen distribution map. So a similar technique is basically used in this set of simulation, and you get this 21 centimeter map from the same in-body and same, let's say, halo map. So now if you compare this particular map with this one, you can see that most of these C2 signal is coming from the black regions of these maps. So the galaxies are, or the halos are located here. So more precisely, let's say if you have incorporated the evolution of the signal along the line of sight, and you can create something called a light cone cube, where one axis of your simulation volume will represent your line of sight axis or the redshift axis. So for example, here the simulation stretches from redshift 6 to 7.2, and this is the 21 centimeter map, and this is the C2 map. So now I want to know what is the level of cross correlation, or what is the level of correlation between these two maps, whether they are anti-correlated or positively correlated or uncorrelated totally. So I can calculate, just like the power spectrum, I can calculate something called cross power spectrum between these two fields, and the definition would be almost same. So earlier in the definition of power spectrum, if you remember, I was taking the fluctuating field or the Fourier transform of the fluctuating field from a particular signal, and I was taking the two k modes, k1 or k2 or k prime or k here as it is shown, and multiplying them and taking ensemble average of that quantity. Such a manner, there will be a Kronecker delta function which will make sure that it is not direction dependent, because the 21 centimeter, sorry, the cosmological signal should be homogeneous, statistically homogeneous and isotropic. So the direction independence is introduced by this Kronecker delta function. So I could define something called autocorrelation of a particular signal, auto power spectrum of a particular signal through that estimator. Here, what I have done, I have just replaced one such Fourier transform of the signal, let's say 21 centimeter signal, with the other signal, that is C2. So S1 and S2 are two independent signals coming from the same redshift. Okay, and their Fourier transforms are being multiplied, and then ensemble average was being taken such that this k and k is equal to minus k prime. That particular condition is held thanks to this Kronecker delta function, and what I will get is this PS1 cross S2, that is the cross power spectrum between these two signals. Now, once I have that, I need to know what is the degree of correlation between the signals, right? So the cross power spectrum actually will tell me the cross power between these two signals as a function of k, or wave number, or inverse of length scale. K is equal to 2 pi by L. L is the length scale that I am trying to prove, right? So On top of that, if I want to know the cross correlation, level of cross correlation between these two signals as a function of length scale or inverse of length scale or k, I would like to calculate something called cross correlation coefficient, or this is similar to the Pearson's coefficient that you have seen in statistics class. So RS1 cross S2 will be my cross correlation coefficient as a function of k, which will be this cross power spectrum divided by root over of individual auto power spectrum of these two signals, right? So that will give me the cross correlation coefficient. By definition, this cross correlation coefficient can vary between -1 to +1. It will never have a magnitude greater than 1. Okay. And if it is -1, that means the signal at that particular k mode, these two signals at that particular k mode are perfectly anti-correlated. If it is +1, then they are perfectly correlated. If it is 0, then they are perfectly uncorrelated. Correct? So that would be the way of interpreting the cross power spectrum. So let us look at this plot. Okay, for the time being, ignore the bottom panel, these three bottom panels. I will not discuss them. H1, H2, H3 represents three different histories of reionization. Let's say my reionization model gives rise to, if I change the model parameter, the reionization evolves differently. How do I probe the history of reionization, or how do I quantify the history of reionization or measure it? Is via this average neutral fraction, by measuring the average neutral fraction from my simulations as a function of redshift, or if there is an observation through which you can basically measure the average neutral fraction of the intergalactic medium as a function of redshift, that will tell you the history of reionization. So H1, H2, H3 represents three different history of reionization, while we are keeping the model same, and we are achieving three different histories by varying the model parameters. So here we have quoted three different model parameters, and I think these three different model parameters were also discussed by Tirthuda while basically the discussion regarding the simulations of 21 centimeter of the reionization. So one is the minimum halo mass that can host a halo. So in this case, we have kept it, we have basically in three different histories, H1, H2, H3, they are of different value. One is 10 to the power 9, the other two are 10 to the power 10 MSUN in MSUN unit. And then there is something called efficiency of ionizing, means efficiency of production of ionizing photon, or ionizing efficiency per unit baryon. So in Tirthuda's simulation, that is represented via zeta, and here it is represented via n ion, the same parameter essentially. So I have varied it 18 and 42, the other two history. And then there is the mean free path of ionizing photons, RMFP, that is the third parameter, which has been varied in this manner in these three reionization histories. So these three reionization histories, so the top panels actually show me the cross power spectrum at three different redshifts. So three different redshifts means redshift 6.8, 6.6, and 6.4. Now, at three different histories, the corresponding neutral fraction value at these three redshift will be different. That's why the neutral fraction value is also quoted besides their redshifts. Now you can see that this blue one is the lowest redshift, and the pink one is the highest redshift, and red one is somewhere in the middle between these two. So you see that at small k mode, so this one is 0.1, this particular tick has 0.1 mpc megaparsec, and this one, let's say 1 mpc megaparsec. And let us just concentrate on the signal between these two, within this range, 0.1 to 1 megaparsec inverse. So around 0.1, the cross power spectrum is higher in case, if I look at the, it is not necessarily higher. Actually, the highest value of the cross power spectrum is observed at redshift 6.6. So at 6.8, it is actually lower than 6.8. But the error bars overlap, so it is difficult to say. But if I move to the next K mode, that is 0.2, it is clearly visible that the pink one, that is 6.8, is higher in cross power compared to 6.6 as well as 6.4. But if you, and that is more or less the trend that you see at other two history models. But if you look at the higher K modes or smaller length scale, the amplitude of uh, this cross power has gone down significantly. Okay, one more important fact is that cross power spectrum, though the auto power spectrum can should always be positive because it's nothing but the variance of the same signal, because cross power spectrum is there, the two signals can be in two different, means the phase difference is actually captured in this cross power spectrum. That's why it can be positive or negative. In this case, actually, these values are negative values. So what I have plotted here is minus of that cross power spectrum, so that everything, because it's in log scale, as you can see. Now, the situation can be a little bit more clearer if I look at my cross correlation coefficient, where, as you can see, the signal is highly anti-correlated if I go to very small K modes. Okay, small K modes means very large length scale. So at very large length scale, these two signals are expected to be anti-correlated. And the level of anti-correlation actually decreases with decreasing redshift. So as we go from 6.8 to 6.4, actually the level of anti-correlation is decreasing. If I just concentrate on the solid lines, forget about the dashed lines for the time being. So the same thing happens actually in the other two history models. The only difference is that the level of the decrement in the level of anti-correlation at largest length scale or the smallest K mode is even higher in other two history models. So it depends on how fast or how slow the reionization is happening. That actually one can find out from this cross correlation coefficient by doing some MCMC analysis or model parameter estimation out of them. But if you go to the small length scales or large K modes, so let us look at K equal to 1 in this universe, it is almost uncorrelated. The signal, these two signals become almost uncorrelated because they are almost close to zero. But in all of these cases, please note that all of these neutral fractions are less than 0.5. If I have plotted it above, let's say, neutral fraction 0.5 case, so let's say neutral fraction 0.9 or so, then it would not be so highly anti-correlated. There, you might even see some amount of correlation there, because the ionized region around these galaxies were not such large at those stages. Okay, so that is this would be the potential observable from these kind of two independent observation of the same era that we want to discuss. Okay, so I will pause the discussion here and we will switch to the hands-on session, because now I have, let's say, essentially introduced you or given you the recipe of how to simulate these C2 line intensity maps, right? So we will follow these equations, that is some sort of empirical model for star formation rate, association of star formation rate with the halo mass, and then how the star formation rate is associated with the C2 luminosity. And we will paint our halos that we find from our n-body simulations using this particular relationship, and will generate such a C2 intensity map. That would be our initial task. Then we will calculate the auto power spectrum of C2 as well as the 21 centimeter signal and cross power spectrum, and this cross correlation coefficient also from our simulated data, and we will plot them. So that would be more or less our task for, let's say, for the next half an hour, and probably for the first part of the next session as well. So I suppose all of you have the Psi server. I guess all of you can see my.
Sir, I have a question. Sir, can you please explain that why the anti-correlation is maximum for large scale, at large scale?
Okay, so Right, that's a very good question. So the reason why anti-correlation is maximum at large length scale. So let us look at this distribution of these C2 intensity map as well as the 21 centimeter map. Let us say, because here we are dealing with very low neutral fractions, right? After the reionization has been halfway through, reionization is about to end very soon, let us say, that kind of state. So maybe we are looking at a portion of the universe or the state of the universe which is somewhere around this region. So now if I compare this map with this map, what we will see that wherever I have at very large length scale. So if I, okay, let's say what is the corresponding length scale of k equal to 0.1 MPC inverse? Let us estimate that first. So 2 pi by L, k is 2 pi by L, right? So 2 times pi by 0.1. It will be something like 62, 63 MPC, right? So let us go back to our map. So the typical length scale that we are looking at, let's say 70 to 100 MPC. So that would be half of this box, roughly. Okay, so the K modes that I am probing at very large, or that are probing very large length scale, will be corresponding to length scale of, let's say 100, 90 to 100 megaparsec or something of that order. So now if I take a smoothing filter, okay, what is smoothing filter? Smoothing filter is nothing but a filter that averages out your signal within a certain length scale. Let us take a simple spherical top hat filter, okay, which has a length in the image plane, which has a diameter of 100 megaparsec. So what it will do, it will average out the signal. If I move that filter at each pixel of my signal, what it will do, it will draw a sphere of 100 megaparsec, which has periodic boundary condition, and add up all the values of intensity of 21 centimeter signal within that or C2 signal within that volume, and make an average of that and associate with that pixel over which it was centered. Now I will move that filter 1 pixel. I will move it to the next pixel, and I will do the averaging again. So now, as you can see, if I keep on doing that, the neighboring pixels will not see that much variation of intensity of the signal, simply because of the large volume, because it's a large length scale averaging I am doing, right? So that large length scale smoothing will basically wash out all the small length scale features in your signal. So now if I try to cross correlate, means essentially when I'm looking at a very small k mode cross correlation coefficient, effectively I am looking at an outcome where the small scale features have been thrown away, only large scale features have been kept. So in the large scale, if you look at it, you will see the ionized regions are of the order of that 60, 70 megaparsec by this time of the reionization, by this stage of the reionization. So whatever C2 signal is coming from a ionized region of 60, 70 megaparsec, they will be totally uncorrelated to the 21 centimeter signal, because there is no 21 centimeter signal coming from that particular volume. So a cluster of galaxies which are distributed, let's say in this region, will have a certain length scale, but within that length scale, you will not see any 21 centimeter signal. So what will happen is that 21 centimeter signal will be coming only from the voids where there are no galaxies at all at the late stages of the reionization, very late stages of the reionization. And if they're in the proximity of any galaxies or any halos, the 21 centimeter signal there will become 0. So this will give you this high anti-correlation. So where you expect 21 centimeter signal at a large length scale, you will not expect, let's say, C2 signal at the same length scale. So that is why you will see these kind of features. Now, on the contrary, if I go to very small length scale, then there may be a probability. So let us think about this small island here. That is okay. Let us zoom it in, then probably it will be easier. Right. So let us look at this small island. Now there is a probability that there is a galaxy somewhere nearby, or there might not be a galaxy somewhere nearby. So if I look at the small patches of 21 centimeter signal of the order of, let's say, few megaparsec, 5, 6, 7, 8, 10 megaparsec, something like that, I will have many such patches, right? But I will not have that many patches of large length scale. So in those small patches, sometimes where you have 21 centimeter signal, there are no galaxies, or even if there are galaxies, they are very faint. So you get a faint C2 signal as well. So you might find a correlation, but there will be samples where you will find exactly anti-correlation as well. So where you are getting 21 centimeter signal, you are not getting C2 signal. So eventually this correlation and anti-correlation will, at small length scale, will basically cancel them out, each other out, and you will find a totally uncorrelated kind of pattern between these two, or uncorrelated kind of dependencies between these two signals. So that is why at very small length scale, they are kind of uncorrelated, statistically uncorrelated. But at very large length scale, they are anti-correlated. Again, the degree of anti-correlation, as you can see, depends on the level of reionization. Again, at the very late stages of reionization, the degree of anti-correlation is actually reducing, simply because of the fact now you have neutral hydrogen islands, which are sometimes the galaxies themselves, or these damped Lyman alpha systems, which are extremely high density regions, so the biased regions of the universe, from where you would expect C2 signal as well. So that's why the level of anti-correlation also goes down as you go to later and later stages of reionization. So it is dependent on the history of reionization or the stage of reionization when you are looking at. Okay. So let us, yeah. So what I would like you to do, first of all, if you all have logged into your accounts, just click on the files. So if you click on the files, you will find this workshop ISI. Click on that. I guess all of you, okay. Before, even before doing that, first of all, when you have created your container, please make sure that you have ticked this one, workshop ISI storage volume created by Dheeraj. So there will be two volumes which are associated with your account. In this case, mine is Suman, but there will be one volume which will not be ticked by default, which is this workshop ISI. So you have to tick it before creating your container, computing container. So you go to your, so to do that, you can go to the computing part, right? I did a mistake. Yes, it doesn't go back. So you go click on that computing thing. Yes. So if you click on this compute button, there will be this kind of a list. If you already have a container where your ISI directory is linked, perfectly fine. You don't need to create another one. If you don't have one with that one linked, create another one with linking this ISI directory. So you just create container, tick this one, give something, some sort of name, and then create the container. Okay. So once you have created the container, go back to the home page once more. So click on the SciServer homepage, click on this file tab. Okay. There is a very easy way to actually copy the things that I want you to copy. So go to the workshop directory, and within the workshop directory, you will find one called Suman. So click on that one, and there is a button called copy automatically. A floating button called copy will show up. So if you click on that, then it will ask you where to copy. So what you should do, you should choose the persistent directory that is associated with your username. Okay. And no, there is actually, okay, stop there. So don't copy the entire Suman thing. Sorry. So enter, because it will take too much time. So enter inside Suman and just click on the codes. Okay. And then click on this copy thing and choose your persistent associated with your username and copy it there, paste it there. So press the paste button, it will copy all these codes to your directory. It's done. So I'm closing it. So now you can go to your own persistent. You can just click on this home button. It will always get back to this particular state. Go to the persistent, go to the codes. You should be able to see multiple directories like this. Are these things more or less? So let me know if you are stuck anywhere in this process. So the next thing that you have to do, you have to again go to your compute tab, click on the particular container that you have created while linking this workshop directory. You need to have that workshop directory linked, otherwise the codes will not run, because there are certain customized packages that are required that I have installed already in this workshop directory. Okay, so this is my basically container that I have named as workshop, and I switch to Jupyter Lab directly. So by default, I will be landing within my persistent directory, which contains the storage, etc., etc. So it is equivalent of having your own home directory in a Linux machine, let us say. So give it some time, it will open up. So remember, before doing all this, you have already copied the codes directory that was there within the Suman directory by clicking on the left square and just by pressing the copy button, then going into your persistent. I already have it copied here, so I am not going to copy again. Then by pressing the paste button. So it will copy things within your persistent, that is within your home directory. Okay, you should not edit the codes that are there within the workshop ISI directory. Okay, because they are kind of a fallback option that if we do something wrong, we will again copy stuff from there. Okay, so if we have done that, and now I can go to my own home directory, yeah, in the persistent, and open my codes directory. Yeah. So as I said, first I will need a density field, matter density field. I need to identify halos or bound objects in that density field. Then I will be able to simulate this C2 line intensity using those halos. Right, so I can click on this n-body directory. So within codes directory, you will find a n-body directory. So this is the n-body simulation directory. And this has been adopted from this particular page. So it is actually available in GitHub. Right. So if you go to this GitHub page of Rajesh Mondal, he has nicely arranged the entire n-body thing. So actually you can later on within your computer or wherever you want to run these codes later on for your research, etc., you can copy or clone it from the GitHub directly. The important factor that you have to keep in mind, so this particular markup page you will find here as well when you access it from this file browser. within the Psi server. So the important factor that you have to keep in mind is that you have to install FFTW3 with certain flags. If you are installing it in your let's say computer, but for the time being, for the demonstration purpose of this session, things are already installed in the workshop directory, so you don't need to install it separately, and they're already linked to this particular code, so you don't need to link them either, and I will show you how they are linked. That's also not an issue. So, but if you are installing it in a standalone machine, so there you have to basically install FFTW3 with these flags enabled: enable float, enable threads, and enable OpenMP. Okay. And once that installation is done, the running of the code, because this is mostly a C program, are done via this manner. First, you compile the code using make nbody_comp, and then you run it by /nbody_comp. It requires some input parameter values, and I will show you how you can set those parameters. So let us first go to our terminal. So this is my own home directory. So any time I can type pwd, it will show me my present location, present working location, and I will go inside my persistent. So I will go to the storage, then meet Suman, then persistent, right? So that will contain all the things. I will go to my codes directory, and I will also go inside nbody, right? Right. So now how does this nbody thing works? There is a nice documentation file within this codes directory. You will see if I open it using the file browser here, persistent, codes, nbody, you will see there is a nbody_doc.pdf. And you can, means the exact directory structure is there in the GitHub page as well. So it is same, identical. I have essentially cloned it from GitHub, nothing else. So this nbody_doc, if you click on that, you will find out all the basic equations and working of this nbody code is documented here. Okay, so I will not go into the details, because what it does is nothing but it initiates a density field using the Zeldovich approximation. So it assumes that the initial fluctuation in matter density are Gaussian random in nature. The phases of fluctuations are Gaussian random in nature, and it basically scales the amplitude of these fluctuations with the initial power spectrum, initial dark matter power spectrum, or that scale invariant dark matter power spectrum at very early redshift, something like redshift 1000 or so. And it creates the, so it creates a Gaussian random field, and then you multiply that particular Gaussian random field with your growing mode to scale it to any redshift from where you would like to start the nbody simulation. So you get a particle distribution or density distribution at a very high redshift, let's say redshift 100 or so, from the Zeldovich approximation. Then instead of using time or year as your, let's say, time step, you use scale factor as your time steps here, because we know that the scale factor and time, or redshift and time, are not linearly related, right? So it is basically wise to use the scale factor as your time step of your in-body simulation. So what in-body simulation does, it basically calculates gravitational force. It goes to one particle and asks what is the gravitational force experienced by that particle from all other particles that are there in your simulation box. And each particle essentially represents some amount of dark matter mass here, depending on how many particles you have in what kind of co-moving volume. So you can actually estimate that. So let's say the co-moving volume is 100 megaparsec, and you have 1 million or 1 billion particle. So you know what is the dark matter density in the universe, because you know what is the omega matter parameter, and you know what is the critical density. So you multiply that volume with omega matter times critical density, you get the matter content of that particular volume. And now, depending on how many particles are you simulating within that volume, you can find out what is the mass of each individual particle, right? And that's how you define the mass resolution. And you can right away say what would be the halo mass that you will be able to resolve. So in this type of simulation, you generally assume that at least if 10 or 20 particles are within a certain, let's say, critical distance from each other, or less than critical distance from each other, then they form a collapsed object or a bound object, and I can designate them as a halo. That is done in the FOF, or the halo finding algorithm, which we will discuss later. But for the time being, when you are calculating the force on one particle due to all the other particles, you are essentially using the distance calculation that is based on your cosmological model. So you need to essentially calculate the co-moving distances and convert them into physical distances, then calculate the force. And then based on this force, you essentially update their velocity, because each particle has an inherent initial velocity to start with. You update their velocity, and based on their velocity, in the next time step, you update their position. And you repeat this exercise for all of those particles, so that all of their positions as well as their velocities can be updated in the next time step. And you do it again for the next time step, and so on and so forth. The time, though I am saying time step, these are essentially scale factor steps that we are taking. And you go on doing this thing. So that is what is being done within the n-body code. It starts with the initial density fluctuations created by the Zeldovich approximation, where I am assuming the density field is the phases in these fluctuations are Gaussian random in nature, and the amplitude of the fluctuation is set by the initial primordial power spectrum. And then I am letting these particles to move around under gravitational field created by the other particles. And that is what this particular code does. So what are the input parameters you will need? As you can guess, you will need, okay, so here is a essentially nice flow chart for this particular simulation. And this more or less explains how this is being done. And I would like you to have a thorough look at it. But it is more fun to run it and do something with it rather than going through step by step of a flowchart. The summary of the flowchart, what I said, is more or less that. It is not something extraordinary. There are subtle differences. For example, leapfrog method is being used at a certain stage for a particular reason. And that is also discussed within this documentation. So now let us start with the input parameters that you may need to run the simulation. So you will see within this code file, code and n-body directory, if you say ls, there is something called input.nbody._com. So that is your input file. So there you have to put all the input parameters. So if I just type more and the file name, it shows me the content of the file. I can even say, I can just press Q, so I will come out of that more command, but still it will stay in my screen. So what is there? So the first thing that you can see here is the random number generator seed. Because we are generating a Gaussian random field, so I need to have random number generators. To initiate a random number generator, you have to pass a seed to that random number generator, and that is given here. Okay, and then the next thing is number of bins, n bin. So number of bins in which the code will calculate the power spectrum. So this n-body code actually calculates and uses power spectrum at a certain number of bins in between. Actually, it does power spectrum calculation of the matter density field. So that is the number of k bins for which you will calculate power spectrum for a given k range, let's say. Then there are some set of cosmological parameters. As you can guess, the first one is the omega lambda, second one is omega matter, then this one is probably small h, Hubble parameter, and the last one is the index of primordial power spectrum, which is close to 1. Okay, and this one is, I think, omega baryon. Yeah, this is omega baryon. This one is omega baryon. This is sigma 8 because I need to scale my input power spectrum, the initial primordial power spectrum, depending on the sigma 8. And then actually I define the number of grids on which I am going to simulate these particles. So I am taking a 256 cube grid to start with. And what I'm doing, I'm not filling all of the grid points with one dark matter particle. I'm leaving one grid empty in between two filled grid points. So this filling factor 2 means I'm leaving one grid empty. It is kind of counterintuitive. It is basically one, it should be 1 by 2. You can think of it in that way. So, but you have to pass it as an integer 2. And then this last number says that what is the spacing between two grids. So I have decided the spacing between two grids to be 0.07 MPC. There is a reason why this is chosen, and you can calculate. Actually, this can be a nice homework for you to understand how this simulation works. That if it is 0.07 MPC, I have 256 grid. So that means the one side of my simulation volume is 256 times 0.07, right? So it is 17.92 megaparsec. So I am simulating a volume, co-moving volume of 17.92 whole cube megaparsec cube. That is my simulation volume, right? Why I have chosen such an odd volume, first of all? Simply because if you choose this grid spacing, you will figure out, and if I leave one grid spacing back in terms of blank, in terms of when I am filling the grid with dark matter particles, that means I will be simulating, so half of the one side, so 256 divided by 2 to the power 3, that would be the number of particles I will be simulating, right? So this would be the number of particles I will be simulating within my volume. So now if you have a volume of 17.92 whole cube MPC cube, then you can calculate how much mass should be there and divide that mass, means dark matter mass should be there, and divide that mass with this number. So it will tell you how much should be the mass of one dark matter particle. And it will turn out somewhere close to 10 to the power 9 MSun. 7 into 10 to the power 9 MSun or 8 into 10 to the power 9 MSun, something of that order. And that is chosen precisely because I want to have the minimum, 10 to the power 8 MSun, something around 10 to the power 8 MSun. So this has been chosen precisely because I want to have a minimum halo mass in my simulation volume, or resolvable minimum halo mass, to be of the order of 10 to the power 9 MSun. So I am assuming that the 10 dark matter particles, when they are within a critical distance from each other, form a collapsed object or halos. And for that, if I choose this grid spacing as 0.07, that gives me exactly that leverage that I will have the minimum halo mass in my simulation will be of the order of 10 to the power 9 MSun. So that is the basic motivation of choosing this particular grid spacing. Next, what are the other things you have? Okay, yeah. So that is basically initial value of your scale factor. So here the scale factor is 0.008, and then they have changed the file a bit. Then there is this NF and O flag. These two things are not there anymore. This has been removed. So the delta A, that is the instead of time step, I mentioned that you will be taking scale factor steps, because the entire, let's say, cosmological evolution can be represented with scale factor, and that is way more convenient to deal with rather than time steps. So
So
this
I have a question.
Yeah.
I'm saying if I don't put the two, I mean, if I don't put the gaps, is it possible to same the get the same mass limits by tweaking 0.07?
You will have even lower, even higher mass resolution actually. Just imagine, because then what you will have how many particles you will have. In that case, you will have, yeah, this many particles, 256 cube particles, right? So now why one grid spacing is left blank?
Yeah.
This has something to do with the sampling theorem. Actually, initially, though we are basically representing them as particles, most of the things are being done in Fourier space in terms of the waves. So the fluctuating field is being Fourier transformed, or the fluctuating field is actually being produced in the Fourier space, and then it is basically Fourier transformed back into the particle space, or the image, the real space, let us say. So there, we know from the Nyquist theorem that you cannot probe a signal if you do not have samples at a certain interval, right? So this leaving gap into your grids while filling it with particles comes from that particular philosophy. In principle, you can fill all the grid spacings, all the grid points with a dark matter particle, but what you will end up with is you will have some sort of spurious power at very small length scales. And to avoid that, and those kind of powers are unphysical. Basically, the in-body simulation will not give you proper kind of mass distribution that one should expect from a dark matter distribution at very small scales, as you will evolve it with time. So to avoid that error, we have to basically sacrifice with the mass resolution. That's why we leave one grid spacing empty while filling the grid with particles. So it has to do with the sampling theorem, nothing else. Yeah.
That makes sense. Thank you.
In principle, you will get a high resolution, higher mass resolution, obviously. Yeah, if you do that. But that might not be a correct representation of the universe at small length scale. Again, at large length scales, things might be still be good enough to work with.
Okay, sir.
Okay, so this is the earliest, the initial redshift scale, initial scale factor where you are starting. So if I choose these values and 1 by A, if I do it, what is the redshift that it corresponds to? It corresponds to something like 124 or 25 in terms of redshift. And at a scale factor step of 0.004, recalculations will be done. Recalculation means the force calculations, the velocity calculations, and updating of the particle position and velocity. That will be done at a scale factor step of 0.004. And how many redshift outputs I want, let's say, that is given by this particular number. If I go back here, so n output is basically the number of redshift outputs you want to have as your snapshots of, in this case, and then you have to, basically list out the values of redshifts where you want the outputs. So in this case, I want just one redshift output, and the redshift at which I want it is 8.5. So it is given as 8.5. So let us edit this file a bit. So you can choose a very light editor, which is called Nano. I think it is there. No, it is not there. So let us use VI. So you should be doing all of this in your home directory's code directory, right? Exactly the way I am doing it right now. So let us change it a bit. Let us say I just want an output. Okay, insert, go to the insert mode, and let us say I want an output at redshift 8. That's it. And then escape, press escape, then colon WQ. So check whether things are written correctly or not. Yes, it is redshift 8. So again, press Q, you will come out of your more. Now, the other thing that I want you to look at, but I don't want you to edit for the time being, is the make file. So this make file actually contains all the compilation commands. I think already you are familiar with some sort of make files that Dhiraj might have shown you. So there actually, as I was saying, that you need to install the FFTW3 with certain flags, and which has already been installed, and there actually the installation was done within this workshop ISI Suman softs lib and include directories, and it so you have access to those directories. If you have created the container by ticking the workshop directory, you automatically have access to those directories. You have read permission, so there should not be any issue to compile. So if you are installing it in your home directory in your computer, then first install the FFTW3 with those flags and locate the path where the FFTW lib file and FFTW include files are kept. So provide the location in this link lib variable and provide the include files location in this include variable. That's all you need to do, nothing else. So once you have done that, you can come out of the make file. As you can see, the nbody_comp, the make, let's say, instructions are already given there. So all I need to do to compile the code is make nbody_comp. So it should compile things in a manner that you can see in the screen. Okay. So once this compilation part is done, because now you have your input files ready, input.nbody_comp is ready, and your compilation is done, so you can execute. So okay, one more important fact, I have kept the simulation, basically number of grids in my simulation and number of particles in my simulation very low, 256, 256, 256, simply because of the fact that I want the run to complete within a reasonable time scale, because we have something like 250 GB RAM in Psi server with 16 cores. So this is a OpenMP parallel code. So it will use all of those 16 cores, and you will see it will be printed on the screen. So I pressed /nbody_comp. It is telling me that my dark matter mass is 1 into 10 to the power minus 2 times 10 to the power 10. So roughly 10 to the power 8 m sun. That is my dark matter particle mass. My box size is 1.79 times 10 to the power 1. So 17.92 MPC. Now you can take a whole cube. The number of threads or cores that it has chosen, because that was the number of threads maximum available, 16. And it has defined some found out some normalization factor for the power spectrum, the primordial power spectrum. Here we use the Hu-Eisenstein power spectrum essentially to generate the initial fluctuation field, and give for a given sigmoid, this is the normalization factor for the power spectrum it has calculated. And there are a few other internal things that it has calculated here. And these are, if you go into the details of the code, if you go through the manual that I have already shown you, that PDF file, you will understand some of these things. But the important factor is that, yeah, so Zeldovich approximation is done. So here the particles are moved using Zeldovich approximation, and it was done within very quickly, within 5 seconds or so. And then there is something called an algorithm is there, which is called cloud in shell algorithm, which is running to calculate the density, and it will calculate all of these densities. Why it is taking so much time? Generally doesn't take. Let me check. Right. So you can always open another terminal or another launcher and just type top and see. Yeah, so it is taking almost all of the CPUs. So 100% of the CPU almost, and it is taking significant amount of RAM. It will take some time to run, I think. Yeah, now almost, no, not done yet, but it will be done very soon, I'm hoping, because I ran it earlier. Yeah, so delta AB is running. Okay, fine. So it will be over very soon, within few minutes. So I would expect yeah. So within 2 minutes 40 seconds, this particular run is done. It has taken 24 scale factor steps. So it has done, let's say, 24 rounds of calculations. 24. It has done this force calculation, position calculation, velocity calculations at 24 steps. And 24 redshift steps or scale factor steps or time steps, whatever you may say. And it took us to reach redshift 8 from, let's say, redshift 125, roughly 2 minutes 40 seconds, which is, I would say, quite reasonable, given the number of grids, etc. we have simulated. So now, once this thing is done, the output will be written on a binary file. So don't try to open that file with an editor. So output will be written into this kind of a file where output.nbody, then the value of redshift where this output is produced will be written at the end of the file name. So you can see it is not that heavy because the number of particles that we are dealing with quite small. So it's something like 49 MB. Now, if you have written this file as an ASCII file, it would have been easily 200 MB or more in size. So the advantage of writing the file in binary is that, first of all, it occupies less space in your disk, and it also easier for your codes, whether it's Python or C, because even within Python is using a C function under the hood to read the files and write the files. So any binary file is actually easier for computer to read and write. So that file input output operation becomes faster and it occupies less space. So don't try to open this file. On top of this file now, because this file now contains what? This file contains, let us go to our documentation. This file will contain, did they say it here? No, no, they didn't say it. So the output file will contain two things. One is there are a fair amount of cosmological parameters and simulation parameters, which will be written as the header of the file at the top of the file. And then the binary data will be mostly about the particle position. So 3 position coordinates, x, y, z, and 3 velocity components, vx, vy, vz, okay, of the particle velocity. So this is the main content of the file. Now, as I said, don't open the file with any editor. Maybe the editor will crash and you won't be able to read anything from the file.